This lesson is on graph transformations, and we're going to talk about all kinds of changes that we can do to our functions. And some of these may be familiar to you. So the first two I'm going to talk about are when you add or subtract a number outside of a function. If you add a number, that's going to move it up, whatever that number is. If you subtract a number, it's going to move the graph down, whatever that number is. When you have that same kind of thing inside, so in this case inside parentheses, because this is just our generic case, it's going to do the opposite. Like normally you think of plus moving to the right, a plus on the inside is going to move you to the left. A minus on the inside you would normally think of as going left, but actually it moves the graph to the right. And this is similar to what we saw because we did these kinds of transformations with our trig graphs. And so it's the same kinds of moves. Also, as before, if you have a negative out front, it is going to flip vertically. If the negative is inside, it's going to flip horizontally. So vertically, the up is going to go down and the down is going to go up. Horizontally, the left's going to go right and the right's going to go left. A couple of the other changes here are when you multiply by a number on the outside or the inside. We did this with our trig graphs. On the outside, that affected our amplitude. On the inside, it affected our period. So think about what those changes did on a trig graph. That number outside affected the amplitude, so it stretched it vertically or shrunk it vertically. So it's doing the same thing here. On the inside, that number changed the period, and you had to divide by that number. So if it was a big number, you actually shrunk, and if it was a small number, you stretched horizontally. And so over here, it's the same kinds of changes. We're just doing it with things that are not just trig graphs. So here's how you can come up with those new functions. If it is a number on the outside that you're multiplying by, you're going to multiply the y values of the points on that graph by that number. If it is a number on the inside, you are going to divide the x values on that graph by that number. Okay? And then, so you may want to highlight, this is y values, this is x values. Okay? This one you're multiplying, this one you're dividing. That's important stuff to remember and to keep straight. A couple of other changes you've probably not seen before and we have definitely not worked with yet in this class are absolute value changes. Now, the y equals absolute value of x graph looks like a V shape, but when you use that absolute value symbol in conjunction with other functions in some sort of composition, then it's going to change the shape of the graph. If you have absolute value bars on the outside of your function, it's basically going to take anything that's negative, has a negative y value, and flip it up, because absolute value turns things positive. So you'll no longer have any graph that's below the x-axis. Everything will be above the x-axis. If the absolute value is on the inside, that means what you're inputting is coming from the positives. So whatever the graph is, you erase the left side, and then you flip from the right. It should look like a mirror image. It should be symmetric across the y-axis at that point. What I want you to notice with all these changes is that if something is on the outside, if we're multiplying or we're adding or we're absolute valuing, all the outside things affect vertical movement. It's either moving up or down or stretching up or down or flipping up or down. All that on the outside affects your y values, and it's exactly what you think it should be. If you multiply by 3 on the outside, it stretches it, just like it should. If you add, it moves it up. The inside is the opposite. When things are changed on the inside, it affects the graph horizontally, and it affects the x values. So when we up here added or subtracted on the inside, it moved the opposite of what we've been taught numerically. When we had the negative on the inside, it flipped it horizontally, so another horizontal change. And then again with that C, when we were multiplying in here, it did the opposite. We thought it might, if you multiply by a big number here, it's actually going to shrink it. If you multiply by a small number here, it's actually going to stretch it. So the inside does the opposite of what you would normally think that it does. Okay, so that's the big rule of remembering how these changes are made. Okay, for our first few examples, we're going to work with this kind of generic graph that I've named f of x. And we have this kind of mountain triangle part looking thing over here, and this is supposed to be almost parabolic, but it's kind of hard for me to draw neatly on here. But I've labeled some of the points. Guys, just because I label these points doesn't mean those are the only points on this graph. All the other places on this line where I could make a little dot, those are points. Okay, it's made up of infinitely many points. I just like to label the special points because if I label the ones that look like something's important about them and I make the changes to them, the rest of the graph will follow. So when I'm given one of these, I start by labeling those points. Okay, we're going to take that graph and then we are going to make these changes and sketch the new graph. The first one I wanted to do is that absolute value on the outside because you have not seen anything like that probably before. And so what that does again is take anything that's negative and turn it positive. If it's positive, like this first part, it's all above the all above the x-axis, it's going to stay where it is. The only thing that's going to happen is this part that's kind of U-shaped is going to flip up and make a mountain over here. So if I graph these, I'm going to label these axes the same way that I had them. That first part doesn't change. So I'm going from negative 4, 0 up to negative 1, 2. And I'm going from negative 1, 2 down to 0, 0. Okay, so that is not changing. The part that was over here is going to just flip across the x-axis. And so that high point, or the low point from here will be a high point now, top of a hill, will be at 2, 2. And it will end over here at 4, 0. So everything that was below is now above, and that's the way that graph should look. Okay, with example 2, I'm doing the situation where you have the absolute value bars inside. And I always start this graph on the right side because the right side does not change. So I'm still going to draw that exactly as it was given to me. So we're at 0, 0, at 2, negative 2, and at 4, 0. Again, that part does not change. I do not use the left part of the original graph. It's like I erase that. Whatever is on the right, I then flip so that it is a mirror image across the y-axis. So I'm going to be at 0, 0, at 2, negative 2, negative 2 to negative 2, and negative 4, 0. So I have two valleys connected here, kind of a W shape. The left side of the original graph is gone, and I have a mirror image from the right. Okay, for our third example, we're going to do the graph of f of 2x. So I'm going to write down what change has been made here. When we have that 2 on the inside, that is a big number, so that is going to be a horizontal shrink because it does the opposite of what we think. And the way I'm going to get this is by dividing my x's by that number. So I'm going to divide the x's by 2. So if I go back to my original graph, the first point was at negative 4, 0. If I divide the x value by 2, I'm going to be at negative 2, 0. My second important point was at negative 1, 2. If I divide the x value by 2, I get negative 1/2, 2. And then 0 divided by anything is still 0. So the first part is going to look like this, and you can tell it's been squished in. The next important point was the bottom of that valley. It was at 2, -2. If I divide the x value by 2, I get 1, -2. And then it came up to 4, 0. So if I divide by 2, I'm going to be at 2, 0. So I'm going to make the U shape over here. And you can tell it's been squished in from both sides. It's a horizontal shrink. Okay, for example 4, we have graph of 3f of x. And that 3 is on the outside, so that's going to change our y values, and it does what we think it should. So it's going to multiply our y values by 3. And when it does that, if you think about it, it should stretch it. So it should be a vertical stretch. So I'm just going to take the original points. The x value of those points will not change, just the y value. The original point, first point was at -4, 0. So the -4 is not changing. 0 times 3 is 0. So actually that whole point is going to stay where it was. The next important point was at -1, 2. So the -1 is not going to change, but with the 2, I'm going to multiply it by 3. So I'm going to be at -1, 6. And then again, 0 times anything is 0, so that one ends up back on 0, 0. And then I try as best I can to make straight lines and make that mimic what the original had. And then I'm going to move to the next part. The important point at 2, -2, I'm going to multiply the y value by 3 and get 2, -6. And then our last one was at 4, 0, and 0 times 3 is 0. So I just have to make a longer curve shape here. Okay, example 5 starts where we're going to actually use our toolbox functions and see what changes are made. So first of all, you have to recognize what the function is and then what change has been made. So this is an x cubed function. So you can look that up on your toolbox sheet to know the shape. That's going to give you the shape. Since the -2 is outside of that x cubed part, that is like subtracting on the outside, that's going to move us down 2. In this case, the inside would be in here. You would have x and things like plus or minus inside. That would be in a parentheses situation. So I know this is on the outside. It's after the stuff has been cubed. So I'm going to take the shape of the x cubed. I'm going to move it down 2. It normally crosses at 0, 0. So now I'm going to cross at -2. And I'm going to make that shape of that x cubed graph. I'm just sketching here, so I'm not going to have a lot of exact points sometimes. Example 6, I have an exponential. An exponential is a little bit different. You're not ever going to have parentheses, so you have to know what's inside and what's outside. The exponent is considered the inside. If it's an outside change, it would be down here on the same level with the base. So the exponent is the inside, and then the same level as the base is the outside. So I know by looking at this that this -2 is considered on the inside. Changes on the inside happen left and right, and they do the opposite of what we think they should. So this means that my graph is moving right 2. The e to the x graph normally crosses at 0, 1. So, and it is kind of slow growing over here and then grows fast after that. So I need to move that right 2. Well, the only thing I know is that one point at 0, 1. So I'm going to move that particular point over. And I'm going to be slow growing before that and fast growing after. And so I look something like this. So if I give you an exponential on the test, I'm going to look for that special point to make sure you've moved it the right amount. Okay, number 7 is, again, one of your toolbox functions, but we have 2 changes. this is a 1 over x graph, but it's been moved. You'll know from your toolbox it's either 1 over x or 1 over x squared. Those are your only options, and since this x is not squared, you're stuck with the 1 over x. The inside is the denominator that's down there with the x. There won't be parentheses on this either. And then the outside is up here, kind of on the level with the whole fraction. So this plus 2 on the inside means I'm going to be moving left 2, and the plus 1 on the outside means I'm going to be moving up 1. Now, with 1 over x graph, I'm going to sketch the original one over here. The 1 over x graph looks like this. It has a horizontal asymptote at 0, the x-axis, and a vertical asymptote at 0, the y-axis. That is going to move as well, those vertical asymptotes. So we're going to move from 0, and they're the easiest thing to move, from 0, left 2, and up 1. So that's kind of where those asymptotes are going to cross now. So you're going to have the vertical asymptote coming down through that point, and the horizontal asymptote going left and right through that point. And that kind of grids off where you're going to make your curves. So this upper curve, it's normally in the upper right, is going to be boxed in kind of up here. And then the lower curve that's in the lower left will be down here. And we can get more specific about this later, but for right now we're just getting the general shape with movement. Okay, number 8. Number 8 is your toolbox function y equals square root of x. Again, you don't have parentheses, but the inside is what's under the square root. So this minus 3 on the inside means we're going to be moving right 3. Then you have a negative on the outside, and outside negatives mean we flip vertically. So vertical flip and right 3. And again, your square root function normally looks like this, kind of half of a parabola turned sideways. Some people call it the shooting star. We're going to take that and move it over 1, 2, 3 and flip it down. Okay, here we're sketching y equals 2 absolute value of x, and we're using that original function y equals absolute value of x, which was our perfect V shape. The 2 on the outside, because it's on the outside, means it's a vertical change, and that would stretch it, so vertical stretch. In order to do that on a graph like this, you have to know some of the original points. So if you think about that original graph, obviously it's going through 0, 0. And if you move in a perfect diagonal on a coordinate plane, if you're going over 1 and up 1, you definitely have the point 1, 1. If you went to back here perfectly diagonal, you would go back 1 and up 1, so you have the point negative 1, 1. We don't have to do a ton of points, we just have to do enough so that we can get the shape of this graph going. So I can take these original points now and do this vertical stretch, which means I multiply my y's by 2. So if I take negative 1, 1 and I multiply my y by 2, I'm going to get negative 1, 2. 0 times anything is 0, so that one stays at 0, 0. And then I can take the point 1, 1 and multiply the y value by 2 and get the point 1, 2. And you can see over here that it would stretch and it would be a little bit steeper now than it was before. And again, I just came up with these points by thinking about that original graph, but I had to have a few just to make my shape right. Number 10 is another example of this. Our parent function is the x squared graph because we have this squared here. And then we have the 1/2 inside that is doing a horizontal stretch, because numbers that are between 0 and 1 are going to stretch horizontally. And that should be the only change. So we're going to divide our x's by 1/2, which when you divide by 1/2 you flip and multiply, so you can think of it as multiplying by 2 if you want to. But because it's an x squared graph and I'm doing these changes that require me to know points, I've got to nail down some points. So if I think about a regular parabola, if I get a few points, again, I know it goes through 0, 0. I can come up with a few more points. If I plug 1 into x squared, 1 squared is 1. If I plug -1 into x squared, -1 squared is 1. So I'm getting the y value by just plugging into y equals x squared. That's not going to help me a whole lot. Those are the same points that I just had on an absolute value, so I'm going to do 2 more. I'm going to do one with an x value of 2 and one with an x value of -2. And to get the y value, I just plug into the function. 2 squared is 4. -2 squared is 4. And of course that makes sense because they're mirror image from each other. Now I have enough points to figure out what should be going on when I stretch it. I'm going to take those points, I'm going to divide the x's by 1/2, which basically means I'm going to be multiplying them by 2. So if I take -2, 4, and I'll multiply the x by 2, or divide it by 1/2, I'm going to get -4, 4. So -4, 4. If I take -1, 1, and multiply my x value by 2, I'm going to get -2, 1. 0 times anything is 0. 1, 1, multiply the x by 2, I'm going to get 2, 1. And then 2, 4 will become 4, 4. Or if you just do one side, you can mirror image and know what the others are. And then you just connect. If you were to graph this one on your calculator at the same time as you graphed x squared, you would really be able to see that horizontal stretch like somebody pulled it from both sides. Okay, this is how that absolute value function works when it's on the outside. So we're not doing the V shape. The x squared tells me that it was like kind of a parabola shape, and then the absolute value is turning it positive. Because it's that absolute value on the outside, that's where we flip anything that was negative up. So I'm going to start by, I'm going to do a dotted version of the graph x squared minus 4. So the graph x squared minus 4 is a parabola moved down 4. And that would actually cross at 2 and -2 if you find the zeros. That's what that looks like without applying the absolute value. The absolute value turns things that were negative positive, but things that are positive stay. So this side that is above the x-axis stays exactly where it is, going in the same direction that it is. Nothing changes about that. What changes is this bottom part flips up. So this graph really is this neat W shape. Okay, that's the absolute value applied to the x squared minus 4. So there's really two changes there. And that concludes this lesson.